Hello, Assalamualaikum and good morning. Welcome to our Computational Fluid Dynamics CFD project. In this video, we will take you through the process of simulating airflow over a flat plate using ANSYS Fluent. Our primary objective is to analyze how airflow velocity influences the formation and behavior of the boundary layer. This project is carried out by a group of 4 members. I'm Saiful, the team leader, responsible for the simulation setup and result analysis. Assisting me is Khadijah, who covers the theoretical background and provide context for the study. Wani handles the geometry design and meshing process, ensuring accurate setup for the simulation. Lastly, Mifzal managed video editing and presentation preparation to deliver a clear and engaging final product. Let's begin by exploring some fundamental concepts of fluid mechanics. The Reynolds number. The Reynolds number is a dimensionless value that determines the flow type. If Reynolds number below than 5 times 10 to the power of 5, the flow is laminar, smooth and predictable. If Reynolds number above 3 times 10 to the power of 6, it's turbulent with chaotic motion. In between, the flow is transitional, moving between the two. Visualizing fluid behavior. Our first objective is to use contour plots and velocity profiles to visualize how fluid flows and how the boundary layer grows. Evaluating airflow impact. We also aim to study how increased airflow velocity affects boundary layer thickness and overall flow behavior. Relating theory to simulations. Finally, we link our simulation results to fundamental principles of fluid dynamics, such as boundary layer theory and turbulence modeling, to ensure accuracy and better understanding. Next, let's discuss the geometry details used in this study. Dimension given. On the left, we see the initial geometry with the given dimensions. The height of the domain is 10 meters, while the object's height is 0.5 meters. Dimension in ANSYS Fluent. On the right, we see how this geometry was implemented in ANSYS Fluent. The dimensions were input accurately to ensure the simulation aligned with the theoretical model. This step ensures that the computational setup matches the intended design for accurate flow analysis. In this experiment, we focus on investigating the effects of airflow velocities at 2 ms and 2.5 ms on the velocity profile and boundary layer thickness. We will walk you through the process step by step, from geometry creation and meshing to setting boundary conditions, running the simulation, and analyzing the results. I will fast forward to the velocity inlet part. Purpose of the velocity inlet. The velocity inlet, which in this analysis is 2 ms, normal to the boundary, to defines the direction and speed of the fluid entering the domain. It assists Fluent in determining the domain-wide flow properties such as pressure, velocity, and turbulence. Okay, why it's configured like this? Use the magnitude normal to boundary option to ensure the flow enters perpendicular to the inlet. Absolute is selected, meaning the velocity is given relative to the stationary coordinative system. The supersonic initial gauge pressure is set to 0 Pascal, implying no additional pressure is imposed at the inlet beyond the atmospheric or default reference pressure. Purpose of the pressure outlet. Used to specify the pressure at the exit of the computational domain. It ensures a well-defined outlet condition and is critical for flow stability. The pressure at the outlet is set to 0 gauge pressure, meaning it equals the atmospheric pressure, default reference. This setup is to make sure of the following. First, a smooth exit of the fluid without unwanted reflections or instability. Second, proper handling of backflow conditions, example given in recirculating flows. Third, the pressure at the outlet boundary is equal to the ambient pressure, 0 gauge pressure. Pressure, velocity coupling. First, scheme, simple. Couples the pressure and velocity fields for solving the Navier-Stokes equation. The simple, semi-implicit method for pressure link equations method is efficient and stable for steady-state simulation. Second, flux type, recurve, distance base, determines how flux value at the cell phases are interpolated. This distance-based method improves accuracy, especially on structured or unstructured grids. This is how the graph plotting goes for velocities of 2ms. We will repeat the steps we performed at the 2ms velocity state and apply them to the 2.5ms velocity state. I will fast forward the video. Flow comparison at 2ms and 2.5ms. At 2ms, the residuals, continuity x velocity and y velocity converge quickly and stabilize after fewer iterations, indicating a steady flow solution. The value drops significantly, reflecting good numerically stability and accuracy in the simulation. At 2.5ms, the residual take longer to converge and show less stabilization compared to the 2ms. This suggests that the higher velocity introduces more complexity to the flow, requiring additional iterations for converge. The continuity and velocity components stabilize at higher residual values compared to the 2ms. From left, contour of static pressure shows a color map of how pressure changes across the domain with red for high pressure and blue for lower pressure. Evaluation. First, velocity profile. At lower speeds, the velocity gradually increases from the surface, creating a smooth profile typical of laminar flow. At higher speed, the flow can become turbulent, creating a steeper profile with more mixing. Second, thickness. Higher velocities reduce the boundary layer thickness because the flow has more energy, making it harder for viscous force to slow it down near the surface. Slower velocities result in a thicker boundary layer as the flow loses momentum more easily due to viscosity. Third, why it happens. The boundary layer thickness and profile are influenced by the Reynolds numbers, which depends on velocity and fluid properties. That concludes our presentation on laminar parallel flow of a flat plate. Thank you.